Okay, so I'll get started. I sent an email, but just in case someone didn't see it, next week we're having 2 guest lectures, one on Tuesday, one on Thursday. The Thursday one will not be recorded, so if you want to see that lecture, you should be here in person. Okay, so today I want to wrap up with approximation algorithms. So we're going to finish FP tasks. This is for we're going to do it for knapsack. 2, we're going to look at F prasses. I'm going to do this for DNF counting. And then 3, we're going to look at semi-definite programming. And we'll look at max cut. And if we have time, we might look at one other application as well. Okay. So let's get started. So last time we saw with knapsack that there was a p-task. Right? A p-task just means for any fixed epsilon, you can get a 1 plus epsilon approximation. Or for knapsack, I guess a 1 minus epsilon approximation. And your running time is a polynomial in n if epsilon's a constant. But with an FP task, we want to say that your dependence on epsilon is also polynomial. Okay, so we want poly n 1 over epsilon dependence for knapsack. And I think actually what we'll get is today, we'll just see it's a very simple algorithm. It'll get you n cubed over epsilon, 1 minus epsilon approximation. Okay. Do we have a scribe today? Good, okay. I did some searching around to see what the best known bound was for knapsack. So it's possible to get, with a different algorithm, a running time of n times log 1 over epsilon plus 1 over epsilon to the 4th. This is due to Lawler in 79. Yeah, I searched around a bit to see if there was anything after 79 where someone improved this, but I couldn't find things. Maybe I just didn't search hard enough. So yeah, there you go for if you want a final project. No, I'm just kidding. Yeah, okay. So good. So let me show you this algorithm. So this is an idea that gets used a lot in FP tasks, which is, so the idea is rounding. So remember the setup. Okay, we have n items. We have a knapsack, first of all, a knapsack of size W, capital W. And then we have n items with weights W1 up to Wn, and also values V1 up to Vn, remember, and the goal is to pack this knapsack. Don't overload it. You can't put more than W total weight in the knapsack, and the items that you put in there, you're going to collect the sum of values of those items, and you want to get as much value as possible. Okay. So the basic idea is, well, what do we know? We know that there is an algorithm with running time NV. All right, so we mentioned this last time. This is via dynamic programming, where here V is just the sum of the VI. Okay, unfortunately, this is not polynomial time, because the running time depends on the sizes of the numbers as opposed to the logarithms of the numbers. Okay, writing down a number v only takes log v bits, so the input is exponentially smaller than v potentially. Okay. So the trick is just to make v small. Okay, so to get fp-task, what are we going to do? We're going to define new values. We're going to set v prime to equal, or vi prime to be n over epsilon times vi over v max. And let's floor it so that it's an integer. Okay, and then run an O of n v prime algorithm. That's going to give us a set. Right? This is going to be an exact algorithm for the new values. Okay. And that's going to give us a set of items, which is the optimal thing for this new set of values. And the claim is just if you use that set for the original problem with the original values, you'll get at least 1 minus epsilon times opt. Okay, so I'll justify that for you. But what's v prime here? Or any bound on v prime? Capital V prime. N squared over epsilon, right? So this thing here, we have v prime is at most n times the max over I of vi prime. And, well, vi is at most v max, certainly. So this is at most 1. So this is at most n over epsilon. So this is at most n squared over epsilon. So this running time is at most what I said, n cubed over epsilon. So that's all there is to it. And the basic idea is something fairly simple. So what's the basic idea? Okay. First of all, we know that opt prime, by opt prime I mean opt, the value of opt in the new problem, okay, after you change these values, opt prime is at least v max prime, right? The maximum value of the vi primes, right? And one of the items actually has value v max, right? So that item will have at least n over epsilon value. Okay. But how much value did we lose in any given solution in this new rounded problem? Well, for each item in a set, we rounded down its value after this multiplication, right? So by rounding down, we at most decreased its value by 1. So, I mean, the basic idea is, I'll make this more formal. After rounding, right? I mean, if there was no rounding, if we just multiplied by some scalar on every single value, then opt doesn't change, right? Every set just has the same multiplicative factor times its old value. But by this rounding, we potentially lose 1 from every value. So after rounding, any set, let's call it S, a subset of the items, loses at most S, which is at most n value, right? Which is at most epsilon times opt prime. Okay, so let's just now make this a little more, very slightly more formal. So claim if dp on rounded instance returns some set A, okay, which is a subset of n, then the value of A is at least 1 minus epsilon opt. The original, if you take the original valuation and compare it to opt of the original problem. So proof. Okay, what's the proof of that? Well, for all sets S, what we said over there, S subset of 1 to n, we know that the value, if you look at, let me write it like this. So alpha, so the value prime of S is at least alpha, the old value of S minus the size of S. And it's at most alpha times the value of S, where alpha is this scaling that we're doing, n over epsilon times V max. Right? That's what I just said over here. We lose at most the size value. So let A star be some optimal set for the original knapsack problem before rounding. Right, so what do I want to show? I want to show a lower bound on the value of A. What do I know? Well, I know that the value of A is at least 1 over alpha times the value prime of A. Right? That's just that inequality here. And then I know that A is the optimal solution to the new valuations. Right? So this is certainly at least 1 over alpha times V prime of A star. Okay. And now I want to go back toward opt for the original problem. So V prime of A star, this is true for all sets. So in particular, it's true for A star. V prime of A star is at least alpha V of A star, which is opt, minus the size of A star. So this is at least alpha times, so this is V of A star, which is opt. This is opt, minus alpha times, or 1 over alpha, sorry, times the size of A star. Okay. And that's certainly at most n. So this is at least opt minus n over alpha, which is equal to, which is at least opt minus epsilon times V max. That's just the definition of alpha. Right? And now V max, opt is certainly at least V max. Okay, so that's it. So are there questions about this FP task? Okay. If there are no questions, then let's be done with knapsack. And before I move on to F-prasses, you could ask, when can I know for sure that there is no FP task? Right? Not every problem has an FP task. Okay, so for example, for set cover, we know you can't beat log n approximation. Not just because of integrality gaps, but there's actually a proof that unless you can solve SAT really fast, which we don't expect, there's nothing better than a log n approximation. Sometimes for some problems, you can't beat a 2 approximation. For vertex cover, it's known that there's a fixed constant. I forgot exactly what that constant is, but it's bigger than 1, that unless p equals np, you can't beat that approximation ratio. Okay, and there's also some more recent evidence that says you can't beat a 2 approximation if you assume some conjecture. But sometimes there are just kind of easy reasons why there's no FP TAS. Okay, so you don't always have an FP TAS. And let's give a very simple example. So bin packing. Okay. In bin packing, what's the input? There are n items with sizes S1, S2, up to Sn. And all those sizes are in the range from 0 to 1. Bins have capacity exactly 1. And then the goal is to pack all items into as few bins as possible. Okay. And you can't cut items up, okay? So you have to put an item fully into a single bin. People have questions about the problem statement. Okay. So it's known that bin packing, as I've stated it here, is NP hard. Okay, and the decision problem of can you pack these items into even 2 bins? Even that problem is NP complete. Okay. So, question: given what I've just told you, do you expect to have an FP TAS for bin packing? Right. You should use at most 1 plus epsilon times the optimal number of bins. So, what would an FP TAS for bin packing mean? Okay. So an FP TAS in a runtime to find this packing is polynomial in n as well as 1 over epsilon. Right? Do you expect to have an FP TAS for bin packing? Why not? Okay.
So you can't find a solution that uses fewer than that many bits.
That uses fewer than, but why can't you?
Because that epsilon is smaller than 1 over n.
Yeah.
Then you would have n importance.
Yeah, right. So the point is, so the reason, so we don't have an FP TAS unless P equals NP. What's the proof of that? If we had FP TAS, run it with epsilon much less than 1 over n or something. And the point is the error in the number of bins you use will be less than 1. And we know the number of bins you use is an integer. Okay, so if I tell you there is a packing using at most 2.2 bins, well, then you know that there's a packing using 2 bins, right? So you could have solved that decision problem with an FP TAS, and it would have been a polynomial time algorithm. Okay, so you don't always expect to have an FP TAS. And I guess the term that's used when you don't have an FP TAS is that the problem is strongly NP hard. Okay. Good. So that's all I want to say now about FP TASes. And I want to move to FPRASes. Okay. So FPRAS, so 2 FPRAS It's like an FP task, but the algorithm is randomized and has some 1/3 chance of failing to find a good solution. At most a 1/3 chance. So I want to give you an example for this as well. Okay, which is DNF counting. Okay, so maybe people remember what CNFs are from 3SAT or SAT, right? So CNFs are formulas written, so it's called conjunctive normal form. D stands for disjunctive normal form. What does it mean? It means that you have some clause. So an input, what does an input look like? It looks like a clause. I'll say what a clause is in a second. A clause C1 or C2 or ... or CM. And a clause, some CI, looks like some x, J1 and x J2 and whatever, and x JR. And some of these might be negated, And right, the satisfiability problem for DNFs is, right, and CNFs, you sort of flip where the ands and the ors are, right? So in a CNF, you would and a bunch of clauses, and each clause would be an or of some number of literals. Okay, in DNF, you reverse that, and we know from, the Cook-Levin theorem that SAT is an NP-complete problem. Okay, so SAT at least is NP hard. How about the decision problem, The decision problem for SAT is if you're given a CNF formula, does there exist an assignment to the variables which causes the formula to evaluate to true? How about for DNFs? If I give you a DNF and I ask you, is there an assignment to the variables which makes this thing true? Right, is that hard? No. Why is that not hard? Well, you solve any clause. So this thing is satisfiable if and only if at least one of the clauses is satisfiable. And then you can just go loop through clause by clause and just check that, basically it's satisfiable as long as you don't have x and not x somewhere, right? Okay. So DNF satisfiability, that problem is in P. There's a polynomial time algorithm for that. That's a pretty simple algorithm. How about DNF counting? Given a DNF formula, count the number of satisfying assignments to the variables. Okay, do you expect that to be easy? Any thoughts?
If you knew that all the assignments are satisfiable, you know that negation is unsatisfiable, so you have a number.
Yeah, exactly. So if you could count the number of DNF solutions, you could solve SAT, right? Because if you have, so this is a hard problem to do it exactly. So the proof that it's hard is that if you have a SAT formula, let's say you have x1, and not x2 and x4 or something. Whoops, this is a DNF. Let's say if a set formula looks like that. And you have some other thing, x5 or not x1 or whatever, right? So you want to know whether or not this thing is satisfiable. This is your input for SAT. Well, if you could count the number of solutions and then you would know whether or not it's satisfiable, because you would know whether the number of solutions is 0 or not, right? So how could you count the number of solutions to this CNF formula? Well, you could negate it, just negate the whole thing, right? And then this just becomes, the negation of a CNF is a DNF, right? So notice that C1 and C2 negation is just equal to negation of C1 or negation of C2, right? So if you have a CNF, so here if you have a CNF, this is now a DNF. And you could have lots of clauses here. And if there are n variables, well, if the number of solutions to this DNF is t, then that means the number of solutions to the negated CNF is t, which means the number of solutions to the non-negated CNF is 2 to the n minus t, right? So if you could count the solutions to the negative, then you're counting the solutions to the original thing. Does that make sense? Okay. So solving the exact counting problem for DNFs is NP hard. In fact, it's even harder than NP hard. It's what's called sharp P hard. Okay, so in fact, I'm not going to dwell much on this. In fact, there's a complexity class sharp P, and the complete problem for sharp P is counting the number of solutions to SAT. Okay, and DNF counting happens to be complete for that class. DNF counting is sharp P complete.
What's the sharp?
Sharp is like number, so it's like counting. Yeah, I mean that's where that name came from. But it's a class that contains NP, so it's basically, so for people who have taken some complexity course and have seen the formal definition of NP, right? In NP, NP is the class of problems where there's a witness that's verifiable in polynomial time. And sharp P, you want to count the number of witnesses, basically. So it's an even harder problem than finding a witness. Okay, so this is a pretty hard problem. But you could ask ourselves, well, can we count number of solutions to DNF up to 1 plus epsilon? So I'm not going to get the exact number of solutions to DNF, to the DNF counting problem, but I'll get some number that's at least 1 minus epsilon times the true number, and it's at most 1 plus epsilon times the true number. Okay. Notice that it's not immediately clear that we can't do this, right? The proof that counting DNF was hard really relied on the exact count, right? Right? We said that basically, if we could tell whether the number of solutions to the CNF is 0 or not, then we would have solved SAT. But if there's some multiplicative error here, then we can't distinguish 0 from non-zero. Okay. So, and the answer to this question is yes, we can. There's an FPRAS. Due to CARP, Luby, And Madras. What year is that? I press, let me, JL89. Okay, and that's what I'm going to show you.
Is there an FP task also?
You mean a deterministic counting? Yeah, I should know this. I don't think so, but let me look into that. Oh, like for example, like is it hard for some complex? Would it imply collapses of complexity classes if that happened? I don't know off the top of my head. I'll have to. I'll look into that. I'm not sure. Yeah.
Isn't the number of solutions also an integer? So why isn't this like similar to the other problem, where because we have an integer, we made epsilon small enough?
Yeah.
Like here we also have an integer. That's our answer, right?
Yeah.
Why is this different?
Okay, so that's a good question. I mean, you could ask the same question for knapsack, right? So in knapsack, let's say that the values are integers, and the weights are also integers. But we have an FP task. So why is that? Right? We know that the answer for a knapsack has to be an integer if the values are integers, right? So why? Right? Does anyone have an answer? Why can we have an FP task for knapsack?
Epsilon have to depend on the actual optimal solution for you to be able to pick an epsilon small.
So let's say that the max weight, let's say the max value of any item is Vmax. We know that opt is certainly not bigger than n times Vmax, right? So what I'll do is I'll set epsilon to be much smaller than 1 over n times Vmax. I'll run my FP tasks. It'll give me some number with fractional error, and I'll just round it to an integer because I know the answer has to be an integer, right? So what's, sorry? It's not polynomial. Why? Right. Yeah. So, right. Exactly. So it's that same issue, right? So, with knapsack, the problem is that you don't want to run in time proportional to the numbers. You want to run in time proportional to the description of the input. And to write down Vmax takes log Vmax bits. So you would have to set epsilon to be too small. And poly 1 over epsilon wouldn't cut it. Okay. And it's the same with DNF counting. It's a similar thing. You can have DNFs where the DNF has size n or something, but the number of solutions to that DNF is exponential in n, right? So imagine a DNF which is x1 or x2 or x3, etc. It has exponentially many solutions, right? The only thing that's not a solution is if all the x's are false. So it has 2 to the n minus n solutions. So if you wanted to get that answer accurately, you'd have to set epsilon to be 1 over that. And then poly 1 over epsilon would be exponentially big. Okay. So the idea behind, the way that we're going to get started developing this Karpelube-Madras algorithm would be to try out the first thing that might come to mind if I tell you come up with a randomized algorithm, right? But there's going to be a problem, and then we're going to have to use a clever trick to get around that problem. So what's one way to randomly estimate the fraction of, so there are 2 to the n assignments. Let's say there are n variables. And n clauses. Sum of the 2 to the n variable assignments satisfy our formula, our DNF formula. Let's say a p fraction. Right, so really what we want to do is we want to estimate p. Right? So are people with me? Okay, so how would you estimate p? Yes, sample a random assignment, a uniformly random assignment. Check whether or not it satisfies your DNF. And do this a bunch of times and take the empirical mean, right? Or see what empirical fraction satisfies your DNF. Okay, so what's wrong with this algorithm?
There's only one assignment that works. You have
Yeah.
to do 2 to the n
Right.
tests.
If p is very small, in fact, if p is 1 over 2 to the n, so there's only one assignment, you're not going to see a satisfying assignment unless you sample exponentially many assignments, right? So a bad example for this is, what if your DNF formula is just x1 and x2 and dot 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 and xn. Okay, there's only one assignment, and you're not going to see it. You're going to think the answer is 0 unless you do exponentially many samples. So really, the problem is that p can be small. So the trick in this FPRAS that I'm about to show you is to rig things so that p is not too small. Okay. So here is the let me just call this KLM. So okay, so what does KLM do? Okay. Let SI be the set of assignments satisfying clause I. And now set U to be, well, not U, let's say B. Set B to be the union over all I from 1 to m of SI. We want to estimate the size of B. Up to 1 plus epsilon. Okay. Now, define B prime to be, how should I put this? The set of all pairs I comma x such that assignment x satisfies clause I. Or if you want to think about it, I don't know, I wanted to write it explicitly so you know what I'm saying. I think some people use this notation, the disjoint union of SIs. Okay, so each satisfying assignment is not written just once in the set. It's written multiple times, once for every clause that it actually satisfies. Okay. Okay. So notice that, so question, we want to estimate the size of B. Is it easy or hard to estimate the size of B prime? Wait, in this, right? I mean, in general, I give you a DNF, right? I give you an arbitrary DNF, which is an OR of a bunch of clauses. A clause is just an AND of some literals, and I want you to compute or estimate the size of B prime. Okay, you don't have to be shy, just yell it out. I see a nod. Okay, so Explain your nod.
Well, it's the sum of the sizes of each of the size, and that's the size I can count because it's just two numbers.
Right. Yeah. So the point is, the size of B prime is the sum of the size of SI, where I goes from 1 to m. And what's the size of SI? Well, this is just 2 to the n minus number of literals in CI, right? So for the literals that actually appeared in the if clause, you know what you have to set them to make this and evaluate to true. And then all the other n variables you can just set to whatever you want. Or all the other n minus number of variables you can set to whatever you want. Okay? So the point is we can actually compute the size of B prime exactly very quickly. So now, instead of estimating this p, let's estimate p prime, which is the size of B over the size of B prime. And then once we get this, we'll just multiply it by the size of B prime, which we know, and then we'll get the size of B up to some error. Okay? So what's a lower bound on P prime? The problem before was that P prime could be too small, right? So now what's a lower bound on P prime? Can P prime be too small? One over m, right? So P prime, note P prime is at least 1 over m, right? Because each assignment in B appears at least once in B prime, and it appears with multiplicity at most m, right? So B prime is at most an m factor larger than B is. Okay, so P prime is not too small. And now, how can I give me an algorithm to estimate P prime? Right, so what we want to do is we want to somehow do something similar to what we did before, which didn't work. Pick a random assignment, and then reject it if it's not in B. The problem is that a totally random assignment is probably not in B, or it might not. The chance that it's in B is really small. So instead, what do we do? Right. We need to pick a random element of B prime and check if a random element of B prime is in B. Right? So pick a random element of B prime and check if it's in B. Well, checking if it's in B is sort of a weird thing to say because kind of the types of the elements of B prime and the types of elements in B. When I say type, I mean in programming languages, right? Like an element of B is a bit string of length n, right? It's a true-false assignment. An element of B prime is not a bit string of length n. It's a bit string of length n together with an index from 1 to m. So what do I mean when I say check if the element of B prime, if this pair, check if it's in B, right? So what's one way, how can I implement this check if it's in B? And then we'll also talk about picking a random element. But how can I check if it's in B? Yeah.
From the I in CX, that is right interesting.
Oh, so the way a DNF is, to satisfy the entire thing, you just have to satisfy one of the clauses, right? So any x in B prime definitely is in this set, right? So I want to, basically what I want, right? What do I want? I want a bijection between B and a subset of B prime, so that it makes sense to check that this element of B prime is in B. Okay, and I'll just spill. Oh yeah. Yeah. So check. So look at it. So what's the bijection going to be? Basically, for every assignment x that appears anywhere in B prime, its representative, which corresponds to it being in B, will be the I such that it's the first time. I is the index of the first clause that x satisfies. Okay? So bijectively map B into the set Ix, so B prime, well, this is bad notation, where Ci is the first clause X satisfies. Right? So each satisfying assignment is counted exactly once now. And we can check that, right? Once we get an element of B prime, we can just now take that X, compare, like run it through every clause, and make sure that that I is the first time it's satisfied. So we can check that quickly. Okay. How about picking a random element of B prime? How do we do that? How do we pick a random element of B prime? How do I choose a clause? Choose any clause? Okay. You mean not randomly, just arbitrarily?
Randomly, yeah.
Randomly? Okay. Uniform, like under what distribution? Uniform? Okay. So we could do that. I don't know how to make a uniform clause work. But okay, you have a suggestion?
Well, instead of uniform, you can just like how much elements there are in each of the clause. And so then you just have a distribution that's based on the weight of each of the clause based on their size.
Yeah.
And then if you have this, then you can pick an element of a random distribution, and it would be like the same as rendered uniformly on all of the elements.
Wait, so, okay, so I think, so yeah, so you said we'll pick clauses like that with probability dependent.
It's going to be the size of the clause divided by the size of B prime.
The size of the clause. Okay, so not quite the size.
SI divided by
The size of SI.
Yeah, size of
Right. Okay, good. So the point is, what are we going to do? We'll first pick a clause I, pick a clause randomly, where the distribution is as follows. Clause I is picked with probability the number of assignments it has over the sum j from 1 to m of size of Sj. Right? So not uniformly, but according to this distribution. Right? And then now, then pick a random satisfying assignment for CI. A uniformly random assignment. Uniformly. Okay. Right. So if you pick from B prime this way, then you will guarantee that the element you get is a uniformly random element from B prime. Now, we already said we know how to compute these things, right? So we can actually do this. The size of SI is just, well, we wrote it somewhere before, 2 to something minus something. Maybe I erased it already. Top? Oh, yeah, there. The size of SI is that, 2 to n minus the number of literals in CI. So we can compute this. We can compute these numbers.
Is that assuming there are no like literal limits?
Yeah, so if you ever have a clause, if you ever have a clause that's ever like x and not x, then you can just throw that out of your DNF because there's no way you're ever going to satisfy that. Okay. And now picking a random satisfying assignment, well, how do you do that for the clause? Well, the literals that are actually in the clause, you set them to what they have to be. And everybody else you just pick uniformly at random. Okay. So that's that. Okay, so that's the entire algorithm. That's going to we sort of sample and estimate p prime. So now we just want to argue that this works. So the final algorithm is sample t elements from b prime. Let p prime, let p prime tilde be fraction of t sampled elements that are actually in B. And then 3 will output p prime tilde times the size of b prime. Are there questions about what the algorithm is? So does anyone have any ideas for how we might prove that this algorithm works well? Okay. Well, I saw it on people's lips, but no one wants to speak it loudly. So the turnoff bound, right? So analysis, turnoff bound, right? So more formally, let x1 up to xt be such that xj is 1 if the jth sampled element is in B, and 0 otherwise. And let x be the sum from j equals 1 to t of xj. So what's the expectation of x? Well, by linear expectation, it's going to be p prime times t. So now, when does this algorithm fail? This algorithm fails if x minus its expectation is bigger than epsilon times the expectation. Right, so this means we failed. We failed to get a good approximation. So what's the probability of that? Well, the turnoff bound says that it's at most, well, the turnoff bound says 2 times e to the minus epsilon squared mu. Mu is the expectation, over some constant. I don't know, 3 or 4 or something. And what's this thing? We said this thing is p prime t. Right? So this is less than delta if t is at least some constant times log 1 over delta over p prime times epsilon squared. Right? And remember, we know that p prime is at least 1 over m. Right? That was the problem before. We could have done the same exact argument in the beginning, where we just sampled random assignments and saw what fraction of them worked. The problem then is that p could have been 2 to the n or something, which means we need at least 2 to the n samples. But the point here is that p prime is not too small. P prime is like 1 over m. So this is just m times log 1 over delta over epsilon squared. Okay. So we take a polynomial number of samples. For each of the samples in polynomial time, we can check whether or not it's in B. We can do the sampling in polynomial time. So this is all a polynomial time algorithm. So that's it. That's an FPRAS for DNF counting. Okay. Questions about? I'm gonna move away now from FPRASs and FPTASs and move to another topic, another approximation algorithms topic. So before we do a switch, are there any questions? So I haven't told you yet how algorithms work to actually solve linear programs. I just claimed that there are algorithms to do it. So next week you're going to see some guest lectures. When I come back, we'll start talking about how to actually solve linear programs. So now that we're in the phase where I'm just claiming certain things can be solved without actually proving it, I'm going to claim that we can also solve semi-definite programs. Okay, so I should first define what that is. So semi-definite programming, I'll just like linear programming is often called LP, this is usually called SDP. So what is a semi-definite program? Okay, good. So SDP. So X, capital X, is an n by n matrix. So linear programming, we're trying to solve for some vector x. Now we're trying to solve for some matrix x. And what the problems look like are minimize the trace of C transpose x. I'll say a second how to interpret this. Such that for I from 1 to m, the trace of AI transpose x is equal to BI. Okay. So just like LP is you minimize C dot x subject to AI dot x is BI for a bunch of different rows of this matrix A. But now both AI and X are both matrices now. And there's also these non-negativity constraints. Okay? And we're going to replace the non-negativity constraints with, well, it's called semi-definite programming, a positive semi-definite constraint. And I'll say what that means. I'll do a little linear algebra review. X is positive semi-definite. And I'll usually write this as X is at least 0 with a little squiggly greater than sign. So known, so you can see a book, there's a book on semi-definite programming. What's it called again? So it's called semi-definite programming. and it's by Vandenberg and Boyd. Okay. That can solve SDP up to, say, L bits of precision in time, poly and ML. Okay, so we're just going to take that as a black box. Just like for LP, I said there are algorithms out there that can solve linear programs in polynomial time. I'm just going to take for as a black box that we can do this for SDP. Okay. And so what is this trace of C transpose X business? So you can prove to yourself. So I'm not going to prove it. So just fact, you can go and, I mean, it's just a computation. The trace of A transpose B in general is just the sum over ij of aij bij. Okay? So really what this is saying is don't view X as a matrix. So except for the last part, which is really something matrix specific, don't view X as a matrix. Just view it as an n squared dimensional vector. And this is really just linear programming, right? So this is C transpose X, where C is also an n squared dimensional vector. This is AI dot X, where AI is an n squared dimensional vector. And then you have this funny constraint at the end where instead of saying that it's a non-negative vector, you say that if you view this n squared dimensional vector as an n by n matrix, that matrix should be PSD. Okay, so that's the difference between SDP and LP. Now, so what does it mean to be positive semi-definite? So the definition X is PSD, positive semi-definite, if for all vectors z, or let's say y in Rn, we have the inequality that y transpose x y is at least 0. Actually, let me just write one more thing, which we're always going to use. It's going to be is a symmetric. And by a matrix. Okay, so claim. I just want to do a little bit of linear algebra review. The following are equivalent for symmetric n by n matrices X. So 1, or let's say A, X is PSD. B, so remember, so another fact from linear algebra is if you have a symmetric real matrix, then it can be diagonalized, and it has a full set of real eigenvalues. This is the spectral theorem. Okay. So B, all eigenvalues of X are non-negative. And C can write we can write X as M transpose M for some real matrix M. Okay, so if these things don't look familiar to you, then for lecture, just take them as truth, and you can find them in pretty much any linear algebra book. Okay, I mean, it basically follows. So look up spectral theorem, okay, and you'll see all of this. Okay, so first of all, I claim that linear programming is really just a special case of semi-definite programming. Okay, so I don't want to go through the details because I want to actually talk about, for our purposes in this lecture and what remains of this lecture, I just want to say that there's this thing called SDP, which can be solved efficiently, and now we can use it for approximation algorithms. Okay, so I don't want to get too much into the theory of how to solve them, et cetera, but I want to say just a couple things about them. So LP, linear programming, is a special case of SDP. Does anyone see why? So suppose I have an LP that looks like this. Any LP, by the way, can be written in this form. Minimize C transpose X subject to AX equals B, and X is at least 0 in every coordinate. I claim that this can be represented as an SDP. Right? Yeah, so exactly. So SDP okay. We're gonna define C to just be a diagonal matrix C1, Cn on the diagonal. Okay. We're also going to define AI as being AI1, AIN, a diagonal matrix. And then we're also going to enforce, we'll also add constraints to force xij equals 0 for I not equal to j. You can add more constraints to force that. Okay. And to say that it's PSD now, to say x is PSD, well, it's a diagonal matrix. So all the eigenvalues have to be non-negative, which means all the entries on the diagonal have to be non-negative. Okay, so LP is just a special case of SDP. And I won't say much more about this, but SDP also, SDP is actually a special case of LP, well, where you have infinitely many constraints. So basically for every y, you can write a constraint where the trace of your matrix now is like y transpose times x should be at least 0. Okay. So if you have infinitely many constraints in your LP, you can represent an SDP. But of course, that's a really big LP. Okay. Okay. So now I just want to say that SDP is now really the same, because of this claim, SDP is really the same as VP, which is vector programming. What do I mean by that? We said that if X is PSD, it's the same thing as saying it's M transpose M, which is saying it's, so right, it's a gram matrix, what's called a gram matrix. It's V1 up to Vn times V1 Vn, which means that if we look at the ijth entry of X, that's just equal to Vi dot Vj. Okay, so this implies, for example, the trace of C transpose X, that's just the sum over all ij of Cij vi dot vj. And similarly for the other constraints that you have, you can write it as just a sum of aij times vi dot vj, right? So vector programming is, well, it's like linear programming, except variables are dot products like this. So SDB can be solved efficiently, so VP can be solved efficiently. Right, and there's no more, once you're solving vector programming, there's no more PSD constraint. Because, I mean, you're already encoding that in the fact that you're using vectors in the first place. They're using these vector dot products. So VP says minimize sum over ij, Cij, vi dot vj, such that for I, let's say for I going from 1 up to m, or let's say for k going from 1 up to m, the sum over ij of ak ij vi dot vj should equal bk. That's what vector programming looks like. OK. So now I want to look at an example of using vector programming, which is the same thing as semi-definite programming, to get an approximation algorithm. So an example is max cut. OK, so the input is a graph G equals VE. It's an undirected graph. And you've probably heard of min cut. Max cut is maximize. Find a cut that has the maximum number of edges crossing it. So goal, find a cut. A cut is just a partition of the vertices into two pieces. Find a cut, which is a partition S and V minus S, maximizing number of edges going from S to the opposite side of the partition. So if you took 124 last term, I think I mentioned a good approximation algorithm for max cut. Has anyone seen any approximation algorithm for max cut? Anyone remember anything? Well, I'll tell you. Just pick a random partition. So for each, have a left set and a right set. For each vertex, put it randomly in the left and randomly in the right. Flip a coin. Probably half it's in the left, probably half it's in the right. Look at any edge. What's the probability that the edge crosses the partition? Well, it's a half. So in expectation, half the edges cross the partition, and you get at least m over 2. M is the number of edges. So let's say this thing is equal to m, and this thing is equal to n. You get at least m over 2 edges. And opt is certainly at most m. So you're getting at least opt over 2 edges. OK? Another non-random algorithm is just start with an arbitrary partition. And as long as there exists a vertex that has more neighbors in its own partition than in the other one, swap it. Okay, so this has to terminate because you're always increasing the number of edges that cross the partition. And if it's now terminated, then that means that every vertex has at least half its neighbors in the opposite side, which means that you have at least m over 2 edges crossing the partition. Okay, so both of those are 2 approximations. You get at least half of opt. And for a really long time, those were the best algorithms until I think it was 95. Was it 95? It was Gomans and Williamson. Yes, Gomans, Williamson, 95. Well, actually, 95 is the journal version. So it was even earlier when they first came up with it. But Gomans and Williamson The journal version is in 95. What did they get? Instead of getting at least half of opt, they showed how to get a 0.878 approximation. Okay? And what is this number? This number is the lowest possible value over all angles in the range from 0 to pi of 2 over pi times theta over 1 minus cosine theta. Okay, so so we're going to see that algorithm. Even though the number looks weird, it's actually a very simple algorithm. It's just that before them, people weren't using SDPs to come up with approximation algorithms. And kind of after they did that, it was a really influential paper. So then people started saying, hey, maybe we could use SDPs for other problems as well. And in fact, they did. And there's something called, so first of all, just like LPs have integrality gaps, SDPs also have integrality gaps. Okay. So I'm going to write down max cut. I'm going to write down max cut not as an integer LP, but I'm going to write it down as a quadratic program with integral constraints. Okay. And you'll see what I mean in a second. We're going to relax it to an SDP by whenever we have quadratic terms like xi times xj, we're going to relax that to vi dot vj. So instead of thinking of xi as being a plus minus 1, we'll think of it as being a unit vector, and multiplication will be dot product. Okay, so max cut, we can write it as a quadratic program. We want to maximize the sum over edges in E, where E in edges from I to j, of I think 1 minus xi times xj over 2. So the point is, and here, for all I, xi is in the set from minus 1 and 1. Okay. So the point is, xi tells you whether on the left side or the right side of the cut, vertex I. Now, if they're both on the same side, the product will be 1. 1 minus 1 is 0. If they're on opposite sides of the cut, then you'll have 1 times minus 1, which is minus 1. 1 minus minus 1 is 2. 2 over 2 is 1. So this counts basically how many edges are crossing the cut. This is a quadratic program. So by the way, max cut is NP hard. So we've also shown that now quadratic programming is NP hard. Okay. So we don't expect to be able to solve this quadratic program unless p equals np. So the SDP relaxation is to maximize the sum over edges in E is ij, of 1 minus vi dot vj over 2. And for all I, vi dot vi is equal to 1. Or SDP or VP, it's the same thing. Okay, so we can solve this thing quickly. Okay, but now we don't get a bunch of minus 1s and 1s telling us left or right in the partition. What we get is a bunch of unit vectors. So now how do we actually turn those vectors into a partition? So the algorithm, the Gomez-Williamson algorithm, is pick a random hyperplane, pick a random R in Rn. By the way, remember from the way we got to vector programming from SDP, remember these VIs were the columns of a matrix M. They're n-dimensional vectors. So what we're going to do is we're going to pick random vectors R in Rn, pick a single random vector R in Rn, and put vertex I in S if the sign of r dot vi is at least 0, and we'll put vertex I in the other side of the partition if the sign is negative. Okay, so pick a random hyperplane, and you're either above the hyperplane or below it, and that decides what side of the partition you're on. Okay. So now, in the last minute, what's the expected size of the cut by doing this? This is just the sum over edges in E of the probability that, let's say E is ij, the probability that I and j are, well, vi and vj are on opposite sides of R. Right? But vi and vj are just two vectors. So we can draw them, you know, they span a two-dimensional space, so we can draw them. They're on the unit sphere. They have norm 1, so vi is somewhere. vj is somewhere. What's the probability that they're separated by this hyperplane? Well, R has to be somewhere in here, right? So for them to be separated, R had to be somewhere in here. So there's an angle theta. So the probability that E is separated is equal to, I guess, well, I'm running out of time. So well, the probability that E is separated is theta over pi, which means that the probability separated over 1 minus vi dot vj over 2 is equal to this 2 over pi 2 over pi times theta over 1 minus cosine theta. Right? Vi dot vj is exactly cosine theta. Okay, and so this is exactly where this ratio comes from. Okay, and then you ask, like, what's the worst that this ratio could ever be? Well, it's the inf over all theta. So I'm out of time, but I mean that's basically how the algorithm goes. Maybe I'll fill in details a little more rigorously in the notes, but that's it. Okay, questions in the last few seconds? Yeah.
When you say opposite sides of R, is it really opposite sides of the hyperplane graph?
Yeah, I mean, I just mean, I mean, what's the probability that what's the probability that the sign of vi dot r is not equal to the sign of vj dot r? So by this I mean, what's the probability that the sign of vi dot r is not equal to the sign of vj dot r?
So in the picture, then R has to be.
R would be orthogonal to the dashed line.
Oh, right. So
That's your plane.
right. Oh, yeah. Sorry. Yeah. So I guess so. So R is the normal to the hyperplane. So I guess what I meant is, so if this is the hyperplane, then in this picture, R would be here, I guess. Yeah. Sorry, that picture was a little misleading. Right, but the point is the hyperplane has to be somewhere in this window in order for you to be cut. Okay. So anyway, enjoy the guest lectures next week.